So for our exponential functions, when we look at the graphs today, we're going to have a function. We're going to look at the actual picture of our graph that we're going to create, and then we're going to talk about a couple key features for these graphs. A lot of them are going to be similar to things that we've seen with other functions that we saw with linear functions in our last semester. One thing I want you guys to remember is that if you are struggling to create a graph, you can always create a graph by making an XY table, okay? That works for any function that we're going to look at in Algebra 1. You can make a table for anything that we'll look at next year in Algebra 2. If you get stuck, make a table, okay? I'm going to show you some, maybe what we want to call shortcuts, some other ways that we can pull information out of our function where we don't have to make a table, but you can always make a table, okay? That's your security net. That's your insurance policy, okay? If you get the quiz or the test in front of you and everything else falls out of your brain, make a table, okay? You can always make a table. So that's where we're going to start for today. We're going to make a table. So here's my function. When I make a table, what I'm doing is selecting values for x to plug in, and then I plug in those values for x and I see what I get for y. In general, when I make a table, I like to pick some negative values, some positive values, and 0. So I'm going to pick -2, -1, 0, 1, and 2. I like to pick stuff that's kind of close to the center, kind of close to the origin. Particularly when we talk about exponential functions, the bigger number I plug in for x, the bigger value I'm going to get out for y. Remember, the first thing I'm going to do is take 3 to some power. So if I pick 20 to plug in for x, that's 3 to the 20th power, right? That's going to be a big number way off my graph. So I like to pick stuff that's lower, kind of close to 0. I also like to pick negative numbers because for some functions that we'll look at, I actually can't plug in negative numbers, and that gives me some important information. For some functions, we can't plug in 0, and that gives me some important information. And then I always like those positive numbers in there too, because again, for some functions, positive numbers are going to give me a problem. And so that's good information to have. That tells me important stuff for my graph. So as I plug these in, what that means is in my calculator, I'm going to type 2 times 3 to the -2nd power. So we're evaluating at a given value of x. Yeah, you can pick whatever you want for x. I have a little bit of a strategy for why I pick what I pick, and that's what I talked about a minute ago. But yeah, you can pick whatever you want. And now this part is what we worked on a whole lot last week. And even last time that we met for class, Wednesday, right? We did this a whole bunch. So this is not new. So we would get 2/9 for our y value there. I think your calculator gives you the fraction as a default. Then if I plug in -1 for x, I would have 2 times 3 to the -1st power, which would give me 2/3. Then if I plug in 0 for x, I would have 2 times 3 to the 0 power, which would give me 2. Then 2 times 3 to the 1st, that would give me 6. And then 2 times 3 squared would give me 18. Again, this you can evaluate on your calculator. So now I'm going to plot these points. Remember, that's what the table gives me. It gives me points on my graph. So at -2, I've got the point -2 comma 2/9. So 2/9 is less than a half. So I'm going to make this down here. We don't have a ton of space in here, but it's less than a half. So I'm going to make sure it looks less than a half. And then I have the point -1 comma 2/3, -1 comma 2/3. That's a little more than a half. And then I have the point 0 comma 2. And then I have the point 1 comma 6. So there's 2, 3, 4, 5, 6. And then 2 comma 18. So there's 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Right about there. So there are my points from my table. And now remember, since this is a graph of a function, I need to connect it because it should be continuous. And then let's talk about some of our key information here. I can see a y-intercept. We have a y-intercept at 2. I can also see my y-intercept from the table, right? The y-intercept happens when x is 0. There's my y-intercept in the table. We didn't get to an x-intercept though. And if I look at my table, I don't have a y value of 0. That would be an x-intercept when y is 0. So I'm going to go to my graph on this one. So I've graphed this on my calculator. I'm going to zoom this in so we can see the graph on our calculator. So here's that same function that I graphed on my calculator. And I get really close to that x-axis, but it's kind of hard to see if I actually have like where that x-intercept would be. Okay, so what I'm going to do is go to my table. Now, what I do want to point out here is that this end of my graph is going up. So it's unlikely I would have an x-intercept over here. Probably back this way when x is negative would be a better chance. Probably where I want to look. So I'm going to bring up our table. And remember, here are the x values, here are the y values. As I look, as my x values get bigger, those y values also get bigger. So again, not looking good for an x-intercept on the right-hand side of the graph. So let's look at the left-hand side when x is negative. There's my y-intercept at 2. And then when x is -1, y is 0.6 repeating, which would be that 2/3 that we found. So let's go a little farther back. So at -6 for x, our y is 0.00274, then 0.00091, 0.00030, smaller and smaller numbers here. And then when x is -12, it's 0.0000, it's like a bunch of zeros, right? Now, that's not my y-intercept. Because if the y value were just 0, it wouldn't say 0.0000. It would just say 0. So if I hover my cursor kind of over that box, I can see that that value comes up there. And can you guys see that? I know it's small, but that e -6 right there, that means that this number is in scientific notation. Okay, so since that 6 is negative, that means I could take this number and move the decimal 6 places this way. Okay, so what I actually have is 0.0000003763, blah, 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 blah. So very, very, very teeny tiny number. Okay, so we're still not there. So as I keep scrolling, again, we're still in scientific notation, still very small numbers. Here, x is -21, and now we have to move the decimal 10 places. Keep going. And as I keep going, again, we're still in scientific notation. For this number, I'm moving that decimal 17 places. So these numbers are getting even smaller, right? But we're still not to 0. If I keep scrolling, right, let me get to there, -60. We're still in scientific notation. And this time I'm moving that decimal 29 places, okay? So I can keep going through this table for the rest of our class period, and I'm never actually going to get to an exponential. That's because exponential functions have a new feature on their graph, something we haven't seen before. Exponential functions have something called an asymptote. This one has an asymptote right on the x-axis. So an asymptote is sort of like a force field on our graph. It sits somewhere, right? It sits at some value of y, and it won't let my graph touch it. It won't let anything touch it or cross it, like a boundary, okay? So that means that my graph can't ever actually touch 0 because I have an asymptote there, which means I can't have an x-intercept. The default position, if I haven't done any transformations, if I haven't moved anything anywhere, the default position for an asymptote is at y = 0. I know that this function has an asymptote at y equals 0 on its graph because as I look at the end of my function, I haven't added or subtracted anything that would shift that graph up or down, okay? So I'm going to write in plus 0 here at the end as my reminder that that's where my asymptote lives. If I had plus 2 at the end, my asymptote would be up at 2. If I had minus 5 at the end, it would be down at negative 5, okay? So you can always tell where your asymptote is by looking at the end of your function. Questions for me so far? Okay, and then here we've got that little definition for an asymptote. So my graph will get really close to it, as we saw with our very teeny tiny numbers. But we'll never actually be able to touch that location of our asymptote, and we can never cross it. So then the last thing we're going to look at for this problem are the domain and range. Remember, domain refers to our set of x values that it's okay to plug into our function. So we could plug in negative numbers, we could plug in positive numbers, we could plug in 0. The only other sort of category that we may have an issue with would be fractions or decimals. We know from last semester that we saw problems where we couldn't plug in fractions. It was just those whole number values that were okay for our problem. So I want you now to try to plug in 1.5 for your exponent here. Or any decimal number, 0.24, negative 3.87, plug in any decimal there. Did you get a number out? Yeah. Was it probably a goofy decimal? Maybe, or a fraction? Yeah. But you were able to get a number out, right? You didn't get an error message? So that means we can plug in anything that we want here. We saw as we plug in more and more negative numbers that our y value gets smaller and smaller. As I plug in bigger values for x, my y value is going to get bigger and bigger, but I don't have any issues with x value. So our domain is anything we want. So we would write that as negative infinity to infinity. I can plug anything I want. Our range are the y values, the output values. What can I get out of this function? So I can plug in anything I want, but I'm going to have some limitations on what I can get out. I'm going to be limited by my asymptote. Remember, this is like our force field that we can't touch or cross. Because I can't touch or cross this, that means I'll never have a y value of 0, which is why we'll never have x-intercepts, and I'll never have y values that are negative. So our range is impacted by that asymptote. So our range here has to be bigger than 0. Since our asymptote is at 0, it's anything bigger than 0. That would be 0 to infinity. All of our graph is going to sit up here where y is positive. And again, I'm using parentheses here because I can't actually have 0 as a value. Questions for me on number 1? Okay, let's take a look at another example. Let's take a look at number 2. We're going to, again, use our table here. So I'm going to pick those same values for x. I'm going to plug them in and see what we get for y. So this would be 2 to the negative second power plus 4. If I type that in on my calculator, I would get 4.25. And then if I plug in negative 1, that would be 2 to the negative first plus 4. If I evaluate that, I would get 4.5. Then I'm going to plug in 0 for x. So I have 2 to the 0 plus 4. That gives me 5. And then 2 to the first plus 4. That gives me 6. And then 2 to the second plus 4. That gives me 8. Now I'm going to plot these. So negative 2, 1, 2, 3, 4.25. -1, 4.5, 0, 1, 2, 3, 4, 5, 6, or 1, comma 6, and then 2, comma 8. I'm going to connect my points. And then the other thing I want you to include when you do an exponential graph is your asymptote. So my asymptote here would be at 4. Since we have plus 4 at the very end of our function, our asymptote will be at 4. And then I'm actually going to go ahead and fill that in here. Y equals 4. Our y-intercept we can see on our graph and in our table. It's at 5. What about an x-intercept for this thing? Why will there not be an x-intercept? Yeah, our asymptote this time is all the way up at 4. We can't even get past 4. There's no way we're getting all the way down to the x-axis. None here for x-intercepts. Now, our domain is still whatever we want, right? We can still plug in more negative values of x, more positive values of x. So our domain is from -infinity to +infinity. And our range is still limited by that asymptote. This time, 4 is our barrier. Our graph is entirely above 4. So our range is going to be 4 to infinity. Again, parenthesis, because I can't actually have a y value of 4. I can get really close, but I can't actually have 4. Questions for me so far? Okay, so we can always make a graph using a table. I can always find points on my graph using a table. But I want to show you how the numbers in our function relate to what we're seeing on the graph. Okay, there's connections here. This isn't just some sort of like arbitrary selection that we've made here that give us these points. There's a connection between the numbers here and the numbers here. So I want to talk a little bit more about what we've seen in these first couple of examples. The first thing that we looked at was the asymptote, right? Anything that I add or subtract at the end is going to be my asymptote in the graph. Now, the next number that I see that we're going to talk about is that front number. So when we talked about these problems last week, or earlier this week even, and we talked about initial values, right? Writing a function based on a real life example, something with a context. We had that coral problem, we had the forest fire problem. Our initial measurement number went here. On our graph, this is the distance between our y-intercept and our asymptote. That lead number is the distance between our y-intercept and our asymptote. So that means this number gives me a point on my graph. If I hop down to this guy here, example 2, I don't see anything I'm multiplying by in front. When we add and it doesn't change, that means we're adding 0. When I multiply and it doesn't change, that means we're multiplying by 1. We actually have sort of an invisible 1 in front here. Notice that the distance between our y-intercept and our asymptote is 1. So that lead coefficient gives us the distance between our y-intercept and our asymptote. And now let's talk about this guy, the base for our exponent, the thing with the power. This tells us how we're changing each time. So when we were doubling the amount of coral we had each year, we put the 2 here. Notice that if I look at the distance for the next point between my asymptote and that point, now I'm at 1, 2, 3, 4, 5, 6. 2 times what gives us 6? 3. That's this guy. If I look at the next point on the graph, remember this was up at 18. This was 18 away. 6 times what gives you 18? 3 again, right? So this tells me as I move forward, how far away from the asymptote that next y value is going to be. Same thing down here. This time it's 2. So I started at my y-intercept with a distance from the asymptote of 1. For that next point, now that distance is 2. For the next point, now that distance is 4. We're doubling each time. You multiply by 2 each time. You see that? Okay. So you can still go back to your table if you need to. But I'm going to have us practice some of these, we want to call them shortcuts, as we're looking at our graphs. Okay. Turn to the next page for me. And then we're going to kind of just summarize some of the things that we just saw. So that number in front, when we were writing those functions the other day, it was that sort of initial amount that we had, that initial value. This is the distance on our graph from the y-intercept to the asymptote. And then the base of our exponent is going to tell us how we change for each point. We're going to call that our growth or decay rate or factor. If we're getting bigger, we would call that our growth rate. If our points are going down, we would call that our decay rate. So how are we changing those y values each time? Now for this next example, I'm not going to start with the table. Okay, I'm going to start by picking information out of that function to see what I should expect for my graph. I like to start with the asymptote. So if I look here at the end, I'm not adding or subtracting anything. So that means my asymptote has to be at 0. So I'm just going to put my asymptote right there at 0. The next thing I'm going to look at is where should my y-intercept go? Well, remember that's our lead coefficient that tells us where our y-intercept goes. It's going to go 4 spots above the asymptote. So 1, 2, 3, 4. There's our y-intercept. And then to find more points on my graph, I'm going to use the base of the exponent, that 1/2. This is telling me how that distance changes each time, that distance from the asymptote. So I start off with a distance of 4. This says multiply that by 1/2 or cut it in half. What's half of 4? 2. So that means for 1 spot over, my distance is now 2. What's half of 2? 1. So for 1 spot over, my distance from the asymptote, this distance right here, is now only 1. I'm going to cut that distance in half each time. Here I've got a couple points on the graph of my function. Now let's compare this to what we would get in our table. So if I pick those same x values I've been picking, -2, -1, 0, 1, 2. If I plug in -2 for x here, I would get 16. If I plug in -1 for x, I would get 8. If I plug in 0 for x, I would get 4. If I plug in 1 for x, I would get 2. If I plug in 2 for x, I would get 1. I didn't have these guys because I didn't go back this way. But we did have 0, 4 and 1, 2 and 2, 1. Same points from our table. And if I looked at my other key information, we had our y-intercept at 4, which was the same as what we had in our table. Since my asymptote is right at 0, I'm not going to have an x-intercept on this one. My domain is again from negative infinity to positive infinity. And my range, again, is limited by that asymptote. My graph is going to be completely above that asymptote. So this is 0 to infinity, since my asymptote's at 0. Questions for me on number 3? Okay, let's take a look at number 4. Number 4 is a little different because I don't have the function to start off this time. We're actually going to create the function from our graph. So we got some points. We have some points on our graph here. I can see my y-intercept is at 3. I don't see where I'm crossing the x axis. We have an asymptote there, it looks like, since we taper down as we get close to 0. So it looks like my asymptote is at y equals 0. That means that we would have no x-intercept. Our domain is still negative infinity to positive infinity. And our range, since our graph is completely above that asymptote, would be anything greater than 0. So 0 to infinity. Now let's take a look at how we can write our function from this graph. So we know our asymptote is at 0. So I'm going to put plus 0 at the end. Now I know that if it's plus 0, you don't have to write the 0. Just like in number 3, they didn't put plus 0 on the paper for us. Okay? If it were any other number though, -2 plus 7, you have to write that. Okay, you have to write how we've moved that asymptote. Then I'm going to look at what's the distance between my y-intercept and my asymptote. So for this graph, that distance is 1, 2, 3. That means 3 is my leading coefficient here, that number in front. And then the last thing I'm going to look at is how are these y's changing? Because that's what's going to go into parentheses with that x as an exponent. So I start with a distance of 3 between my point and the asymptote. And then my next distance is 1, 2, 3, 4, 5, 6. 3 times what gives us 6? 2. So that means 2 is the base for my exponent. Questions for me on number 4? Okay, so let's take a look at a couple more problems on pages 9 and 10. Notice for your graphs on pages 9 and 10 that you actually have your asymptote sketched in there. It's a dashed, a little bit blurry line, the one that looks a little bit thicker. So if we take a look at number 1, we've got our asymptote here. We've got our graph. We want to write an exponential equation for this function. So I'm going to start with y equals, and then since I can see the asymptote really clearly, I'm going to write my asymptote. So that's at 1, 2, 3, 4. I went 4 down, so -4. The asymptote is at -4. The next thing I'm going to look at is what's the distance between my y-intercept and the asymptote. 1, 2. So my lead coefficient is 2. And then the last piece of information I need The last thing I'm going to fill in here would be what's the rate of change that I have here. So for that first point I looked at, my distance is 2. For the next point I'm looking at, my distance is 1, 2, 3, 4, 5, 6. 2 times what gives us 6? 3. Yes. Well, remember, this isn't actually the y-intercept that I'm writing here. It's the distance between the y-intercept and the asymptote. Does that make sense? So in some cases it is. So I'm going to put my tree down here and then we'll finish that thought. So the comment we had was, shouldn't this number be -2 since our y-intercept is -2? And that's a good thought. But remember that this green number here is measuring the distance from the asymptote. Now, if our asymptote is at 0, like it was for this last problem, that number ends up being the same as our y-intercept. But since our asymptote isn't always at 0, I don't want you guys to think that this number will always be the y-intercept. Does that make sense? Okay. But that's a good observation and a good thought. Okay, so that was number 1. We wrote a function from that graph. We're going to do it again with number 3. So again, I'm going to kind of highlight our asymptote here just to make sure it's really clear where that is. And then we're going to write our function here. I'm going to start with the asymptote. Time our asymptote is at 1, 2, 3. It's at +3. So I'm going to put a +3 at the end of my function. And now I'm going to look at the distance between my y-intercept and my asymptote. My distance this time is 1, 2, 3, 4. But this graph is a little different than ones we've seen so far. For every other graph that we've looked at before this one, our function was always above our asymptote. This time our function is below our asymptote. So we sort of flipped their positions, right? It was asymptote and then function, and now we're like this, asymptote on top and then function on bottom. So what do you think we need to do to this number? Yeah, right? That negative lead coefficient in our transformations flips our function. So that's what we need here, okay? The other way that you can think about this, in our last example, our y-intercept was 2 spots above the asymptote, so +2. Now we're 4 spots below the asymptote, so -4. And then the last piece that I need is the base for my exponent. So I know this distance is 4. Let's look at our next distance. That's 2. How do I get from 4 to 2? Multiply by 0.5. We cut it in half, right? And then the next distance is 1. So 2 cut in half gives us 1. So this would be a half. Or if you like the decimal version of 0.5 better, that's fine too. Questions for me on numbers 1 or 3? Okay, I want to look at one more problem together. Hop over to page 10 for me, please. We're going to look at number 7. We're going to create our graph this time. I'm going to use those same properties from our function that we used on the last couple of graphs, okay? Now, if you are still feeling a little unsure about pulling that information out of our function, what can you do? Ask questions, that's great. What's the other thing that you can do? If I'm not sure about a graph, how can I always make a graph? Make a table, yep. So as I look at my function, I'm going to look for my asymptote. I have a +4 at the end. That means my asymptote is up at 4. So 1, 2, 3, 4. The next thing I'm going to look at is that leading coefficient. How far away is that y-intercept from our asymptote? So this is a -1. So that means my y-intercept is going to be 1 point below my asymptote. Just like that last example we looked at. We were below, and we said that was a -4. Same idea here. Since I'm seeing a negative number, that means I want to put my y-intercept below my asymptote. And then the last thing I need to know is what are some more points on this graph? So to find more points, I need to know how I'm changing this distance. So we're starting with the distance of 1. And then this is telling me to multiply by 2. So 1 times 2 gives me 2. So my next distance should be 2. My next point should be 2 units from the asymptote. My next point over, 2 times 2, multiply by 2 again, double it again, would be 4. 1, 2, 3, 4. 4 units from the asymptote. If I wanted one more point on here, as I go one more spot over, I'm going to again have to double that distance from the asymptote. So there's 4, 5, 6, 7, 8. There's my graph. Don't forget to connect your points so you have your smooth continuous curve. Questions for me on number 7? Okay, your homework are the remaining problems on pages 9 and 10. Okay, so finish up pages 9 and 10.